Okay, in this video we're going to talk about some definitions and theorems about global or absolute extrema of multivariable functions. So we have a couple definitions here. These definitions should look pretty similar to the definitions we looked at for local maximum and local minimum. So I just want to emphasize here what is different. So we've got a function defined on a domain containing the point x naught, y naught, z naught. We say f has a global or absolute maximum at that point if the function outputs at that point are greater than or equal to the function outputs at other points. That's the same as what we looked at before. What's different here, though, is we're not just talking about in some neighborhood near x naught, y naught, z naught, but we're talking about for all domain points x, y, z. So what we're looking for here is the largest function output for all function outputs. So this function output here is greater than or equal to all the other function outputs. All right, the other important thing about this definition, as with the other definition that we talked about here, is that this just says that the global or absolute maximum is at this point. If I want to actually find the absolute maximum, we would say that the absolute maximum value of the function is the function output at that point. So again, be careful about how you're being asked the question. Are you being asked to find the locations of the points where the extrema occur, or are you being asked to actually find the actual extreme values of the function? Okay, second definition here is about minimum. Really the only difference there is that we've got a less than or equal to inequality. Again, if we're talking about a global or absolute minimum, we would be looking for the function outputs that are less than or equal to all the other function outputs for the whole function. All right, the theorem that you see here, Extreme Value Theorem, you had a similar theorem from Calc 1. And actually, the way I've stated it here, it's actually exactly the same as the theorem in Calc 1. In Calc 1, if you were thinking about a function f of x, and you're thinking about that function being continuous on a closed and bounded region here, you would be thinking about a function being continuous and a closed and bounded set of domain points for a function just f of x. You'd be talking about that function being continuous on some closed and bounded interval, a to b. So that's probably how the theorem looked when you saw that for Calculus 1. Instead of using the words closed and bounded region, they might have used closed and bounded interval, a to b. But the theorem is really the same theorem. If we have a continuous function and we're interested in looking at that function on a closed and bounded region, then the function takes on both an absolute maximum and an absolute minimum value on that region. Okay, so the next part that we'll look at is how to actually find those values. Okay, so this is really just a summary of a few theorems that we've looked at here. To find the absolute extrema of a continuous function on a closed and bounded region R, first you want to start by finding the critical values or critical points of the function that are on the interior of R. And so how you find critical points for a multivariable function would be looking at where the gradient vector is equal to 0 or does not exist. And the other important point here is that you may not be looking on the entire domain of the function. You might be looking on some restricted region that you're interested in. So you need to discard any points that you get that are critical points that are not actually in the region you're interested in. All right, essentially what we're going to be looking for here are the highest and lowest function outputs. So instead of using some first or second derivative test to distinguish between max and min points, what we need to figure out is not just do we have a max or a min, but is this the biggest max or the smallest min for the whole function. I'm going to skip down here to C for a moment and talk about that. This is the same as what you did in Calculus 1. You found critical points and then you evaluated the function at all of the critical points you found and at all the boundary points. So in Calc 1, the critical points would be just whatever critical points you found that were in the interval. And then for your boundary points, if you're just looking at a closed and bounded interval, then you just evaluated the function at each of the end points of your interval. So that would have been what you did in Calc 1. The issue for Calc 3, though, is that you don't just have two boundary points, you have infinitely many boundary points to consider. So the big deal difference here for multivariable functions is kind of this middle part, thinking about what's happening along the boundary. So you're going to find the points on the boundary of R at which f may take on its extreme values. So there are a couple of ways to do that. One way to do that is to substitute the boundary equations into the function. And then that'll allow you to essentially reduce the number of variables, and maybe it turns into a single variable absolute extrema problem. Most of the ones that we'll look at will turn into that. There's also another strategy that you can use, which is actually in the next section of our textbook, which allows you to handle situations where you have many variables and maybe substitution perhaps doesn't work on some of those problems. So we'll learn another strategy in the next section for handling many variables, and that method's called Lagrange multipliers. So the first examples we'll look at, though, we're going to actually use substitution for the boundary equations. All right, so in the next video, we'll look at some examples.